Welcome to the Ontario High School video podcast, Quantitative Problem Solving for Gaseous Systems. That's quite a title. We're going to look at pressure, volume, temperature, and mole calculations, which we kind of abbreviate as PVT-N problems. And this is part one, so hold on. There are several gas laws of interest to us. We're going to start off with Boyle's law, which relates volume and pressure at constant temperature and amount of gas in moles. And notice the symbols for these. Volume is represented by V, pressure by P, temperature by T, and then moles is represented with a lowercase n. The mathematical description of Boyle's law is P1 V1 is equal to P2 V2, or pressure times volume, PV, is equal to a constant, K. So PV equals K. When you have a product equal to a constant, this represents an inversely proportional relationship between pressure and volume. As pressure increases, volume decreases. As pressure decreases, volume increases. Charles' law relates volume and temperature at a constant pressure and amount of gas in moles. The mathematical description for Charles' law is the ratio of V1 over T1 is equal to V2 over T2, or the ratio V over T, volume over temperature, is equal to a constant K. When you have a ratio, such as V over T equal to a constant, it represents a direct proportion. If you increase the temperature, you increase the volume. If you decrease the temperature, you decrease the volume. Again, the key to this also that you have to account for is that the pressure and the number of moles of gas must be constant for Charles' law to be used as a descriptor. Our next gas law of interest is called Gay-Lussac's law. It relates pressure and temperature at a constant volume and number of moles of gas. The mathematical description is P1 over T1 is equal to P2 over T2, or the ratio of P over T is equal to a constant K. Since the ratio is equal to a constant, this represents a direct proportion. If you increase temperature, pressure will increase. If you decrease temperature, pressure will decrease. Please note that the temperature, when you use it in gas law calculations, must be in Kelvin and not in Celsius. We'll also be mathematically describing the relationship between pressure and the amount of gas particles in moles of gas, and this will take place at a constant volume and temperature. So the mathematical description would be P1 over N1 is equal to P2 over N2, or the ratio of P over N is equal to a constant K. Since it's a ratio equal to a constant, this represents a direct proportion. If you increase the number of moles of gas, you'll increase the pressure. If you remove gas from the system, the pressure will decrease when volume and temperature remain constant. We want to be able to predict the changes that will happen, and the way that we can help ourselves with that is by developing an organizing chart to keep track of all the changes in gaseous systems, and we're going to call these IFE charts. I represents the initial state of the system, F represents the final state of the system, and E represents the effect of the change in the system. Please note all temperature entries into an IFE chart need to be in Kelvin, and in order to convert from Celsius to Kelvin, all you have to do is add 273 to the Celsius value. In order to describe the use of an IFE chart, we're going to look at a sample problem. So here we have a sample of gas that occupies 150 milliliters at 25 degrees Celsius. We want to know what is volume when the temperature is increased to 75 degrees Celsius. In this situation, the pressure and the number of moles of gas are kept constant. So when that is true, then we're looking at a Charles' law situation. So if you take a look at the chart, across the top we have spaces for pressure, temperature, volume, and number of moles of gas. Down the side we look at the initial conditions, the final conditions, and then we predict what our effect will be. So in this case, because there's no comment on pressure and the number of moles of gas except they're constant, we just put an X in those, representing that we really aren't going to use them. And because they're kept constant, there's no effect on them from the change in the system. So we'll just put no change, the delta sign representing the word change. Now, we're changing our temperatures from Celsius to Kelvin. So our initial temperature is 298 Kelvin. Our final temperature is 348 Kelvin. Our initial volume is 150 milliliters, and we want to find our final volume, so we put a question mark in there. Notice that the space for the effect of the change in temperature when we initially set up our data table is left blank until we can think that through. We want to complete our IFE chart before we do the mathematics to solve for what the final volume will be. So what we have to consider is that we have a situation where we're relating temperature and volume, and we have a change in temperature where the temperature increases. We know that pressure and the number of moles of gas are the same, so the gas law of interest to us is Charles' law. In Charles' law, we know that the ratio of volume to temperature is equal to a constant, meaning that's a direct proportion. So if I increase the temperature, then I must increase the volume for that to be true. So when we predict our effect on the volume, knowing that if the temperature increases, the volume should increase, and so we put an upward arrow to represent the effect of the temperature change on volume. We're now going to solve this problem using the predicted effect. If pressure and the number of moles of gas are constant, then increased temperature will lead to an increase in volume. This is consistent with Charles' law, so we're going to multiply the initial volume by the ratio of the two temperatures. Since the volume must increase with the temperature increase, the ratio should have the higher temperature, 348 Kelvin, on top in the ratio. The lower initial temperature of 298 Kelvin is on the bottom. So here we're going to show the actual math. Again, we're going to multiply the initial volume by a ratio of the temperatures that's going to ensure that our final volume reflects an increase and not a decrease. So the ratio of the temperatures has to be greater than 1, which means the higher temperature must be on top in the ratio, the lower temperature on the bottom. So we take 150 milliliters times the ratio of 348 Kelvin over 298 Kelvin. When we do this, the Kelvin units will cancel and we'll be left with milliliters as a unit, which means a unit of volume. And it's very important to know again that since the effect of the temperature change on the volume is to increase the volume, since the temperature increased, the ratio has to be set up so that the ratio is greater than 1. So that's what we've done here. And note that the temperature units, Kelvin, cancel. Final units are milliliters. The predicted effect will determine which value goes on top in the ratio. Make sure your predictions are consistent with the gas laws. Let's look at another problem. Here we have the pressure in a bicycle tire is 85 pounds per square inch at 27 degrees Celsius. The bike is ridden up at Tall Mountain where the temperature is -3 degrees Celsius at the top. What is the pressure in the tire on the mountain top? Now, one of the things that you want to think about here is that we're talking about pressure and temperature specifically mentioned. It's a bicycle tire, so volume is going to remain constant in that as long as there's no leak, and since no leak is mentioned, then you have to assume that the volume remains constant throughout. And also the number of moles of gas, if they filled the tire with gas and there's been no leak, then the amount of gas in the tire should remain consistent. When you're looking at a problem where you're relating pressure and temperature and volume and the number of moles of gas are kept constant, that would be described by Gay-Lussac's law. As with any gas law problem, we want to write an IFE chart. So we're going to fill in our values. Our initial pressure is 85 psi. Our initial temperature is 300 Kelvin. Our volume and number of moles, we're just going to put an X there since they're not going to change or be affected by this. Our final pressure, we put a question mark. That's what we're going to solve for. Our final temperature is 270 Kelvin. And when we look at the effect, we know that our temperature has decreased, so we put a downward arrow in that slot. And then we have to look at what the effect of a decreasing temperature would be on pressure. For that, we have to remember the relationship from Gay-Lussac's law, and we'll talk about that more as we look at the next slide. As we look at predicting the effect of a change in temperature on pressure, it refers to or is described by Gay-Lussac's law. And if you remember, the mathematical description of that is the ratio of pressure over temperature is equal to a constant K. This means it's a direct proportional relationship between the two values. If temperature decreases, Gay-Lussac's law would predict that the pressure would decrease as well. So we put a downward arrow in that slot. Now, when we multiply the pressure by the ratio of the temperatures, because the pressure must decrease, the ratio of the temperatures that we're going to use has to be less than 1, has to be equal to a value less than 1. So in that ratio, we're going to put the smaller temperature of 270 Kelvin on top with the larger temperature of 300 Kelvin on the bottom. So here's our mathematical setup. We take our pressure and multiply it by the ratio of the temperatures set up so that we show the effect of a decreasing pressure because temperature is decreasing. The lower temperature of 270 Kelvin is on top in the ratio. The higher temperature of 300 Kelvin is on the bottom. We multiply that ratio by 85 pounds per square inch, and it gives us 76 pounds per square inch. Our IFE chart, we predicted that the pressure should decrease, so we set this up correctly. The kelvins cancel. We're left with psi as a unit. And again, note that decreasing temperature results in decreasing pressure consistent with Gay-Lussac's law. The ratio of temperatures is set up so that the lower temperature is on top of the ratio, resulting in a correct lower pressure value at the end of this. So that is how you do this problem. Well, we're at the end of part 1 of our series on gas law problem solving. I want to leave you with a quote from a great author, Mark Halperin. "Justice can sleep for years and awaken when it is least expected. A miracle is nothing more than dormant justice from another time arriving to compensate those it has cruelly abandoned. Whoever knows this is willing to suffer, for he knows that nothing is in vain." I wish you well.